these applications and these markets will start to exist because of the ability of because of the existence of neuromorphic processors like Pulsar and the capabilities that they bring to the table.
On this episode of Embedded Insiders, we're joined by Sumit Kumar, a co-founder and the CEO of Inotera Nanosystems, to discuss spiking neural networks, specifically how SNNs are powering AI systems today and how neuromorphic computing architectures support the hardware-software co-design process. Next, Rich sits down with marketing director at the Wireless Power Consortium, Paul Golden, to discuss the company's latest version of its charging specification, increasing the charging level from 15 to 25 watts. But first, Ken and I are sharing our thoughts on the upcoming interview about how spiking neural networks are designed to analyze motion, sound, or sensor input directly at the edge. Hello, everyone, and welcome back to the Embedded Insiders podcast. I'm Assistant Managing Editor Tiara Oliver, and I'm here as always with our Editor-in-Chief, Ken Briota. How are you, Ken?
I'm great, Tiara. I'm bright-tailed and bushy-eyed here in a nice sunny New England morning. Although it seems like we're gonna get almost above freezing today, so it's a balmy 22 degrees right now. So it's real nice out.
Wow. Yeah, I meant to ask you about the weather over there on the East Coast this week because I've been seeing like the news releases of people like raiding the grocery stores for milk and all this stuff because of
Well,
the snowstorms.
you got to have your milk and bread sandwiches. You know, it's so important to
For sure.
to run out and buy milk and bread right before the power might go out. People
Yeah.
are so dumb. Sometimes they just panic. They don't know what to do. But the grocery stores were fine. There were a few like if you wanted specific like nice cuts of meat and stuff, maybe they were sold out of that because they didn't bother to resupply because the grocery stores didn't know if power was going to go out. Of course, they've all got generators and everything, but yeah, it was fine. We got at my house, I don't know, maybe 14 inches, something like that. Not a lot.
Okay.
I mean, it's a good amount of snow, but nothing unmanageable.
Yeah.
And we shoveled throughout the snow fall and then finished it off the next day. So nothing terrible here. I know
Nice.
that I mean we're used to it also. Other parts of the country are struggling a bit more, and I hope that it gets warm for them soon, although it
Yeah.
doesn't look like it's going to.
Well, over here in Phoenix, we're doing pretty good. Chilly, but definitely can't complain compared to the rest of the world. So,
What do you mean by chilly? Are we talking, 60 degrees chilly or?
I mean, like early in the morning when I'm taking my dog out, it might be like a high 40, high 40s, 50s later on, but then we jump right back into like 60s and 70s. So can't complain at all.
Incredible. It was in the early morning today. It was, let's see here, around like 9 degrees.
Mhm.
If it or right around sunrise. I've just looked. So yeah, it's great.
Nice.
Anywho, none of this is relevant to embedded technology unless someone out there is inventing a weather machine, in which case I encourage you not to. That sounds like a bad idea.
Yes. I don't know a good segue, but we'll just jump into it. So yesterday I did an interview that was pretty cool. I would say more complicated than I can get into so much detail about, but that'll be the next segment. So I encourage everyone to stay tuned. But it was really interesting. It was with Inotera, and it was basically about how brain-inspired AI is supporting the future of intelligence.
Very
Specifically, a
cool.
new class of processors called spiking neural networks that are designed to mimic spikes in the brain.
That's really, really cool. So the idea is to copy the neural architecture for signal transmission, basically.
Yes. So starting out in our interview, and I encourage everyone to actually go check out the video podcast that'll be posting in conjunction with the audio. But we had a cool slide in the background, and he basically displayed an image of, I believe it was, I can't remember if it was an animal or an insect. I know he referenced both, but started out showing me an image of the spiking in their brain when they're, hunting for prey versus when they're um, avoiding a predator, things like that. So I thought that was like a
Yeah.
cool way to start out an interview, especially in this space. That's not how we usually like jump into a topic. So
Yeah.
immediately caught my attention and I was like, okay. But yeah, basically the
Yeah.
timed bursts in the brain that turn into sensation of spikes or
It's
something. I
really
don't even
interesting. Were
yeah.
they so and this was Sumit Kumar, right? That you were talking to, the CEO of Inotera, is that right?
Yes, yes.
Yeah. Really interesting person. I'm sure the interview is going to be really great to listen to, but that's really cool. It sort of reminds me a little bit of like, and it's a different field and a different thing, of the idea of synthetic data sort of modeling itself after organic data for predictive and experimentation purposes, and filling out data sets that are incomplete and stuff like that. It almost feels like creating a synthetic neural network is so that these spikes work in the software. It's very cool. I look forward to hearing the interview.
Yeah. Encourage everyone to stay tuned. And of course, remember that we are dropping video podcasts on our YouTube. So be sure to check those out, especially with this one. Like I said, there's a great slide in the background that accompanies everything that he's saying. So I think it'll be really helpful for those who are interested.
Nice. Yeah, the video podcasting is really exciting that we're going to do this year. So make sure you're subscribed to us, not just on your favorite place where all great podcasts are given away, but also on YouTube, so you can check out the video version and sometimes see our faces, which is fun.
Yeah. And then also with audio, I know there might not be too many platforms for everyone to comment, but I feel like now that we're posting on YouTube, I feel like that's the easiest way to comment on a video. Everyone knows how to comment on YouTube and all of that and share. So
Yeah,
I feel like we should get some more people commenting on our videos, letting us know what you guys want to see, what you like, what you dislike. So we want to engage with you guys so much more. So let us know.
absolutely. And we always respond to comments. And get in, we love to get in the comments around here, so
Yes.
so get in there and let us know what you think. Thank you so
Sounds
much,
good.
Tiara.
Now, here's Sumit Kumar of Inotera Nanosystems.
Sure. So my name is Sumit. I'm one of the co-founders of Inotera. I serve as the company's CEO. My own background is in microprocessor design. It's something which I've been doing for about 18 years. I have a PhD in the space from the Delft University of Technology. I was with Intel, basically building processors going into camera phones, and subsequently developing R&D programs for the European Commission to bring next generation intelligence into automated vehicles. We set Inotera up in 2018 as a spin-off from the Delft University of Technology, commercializing about 10 years of research into brain-inspired computing and energy-efficient computing. And the company was born with the objective of bringing very efficient brain-like intelligence to sensors so that we can process the world's sensor data at the source as soon as it's captured.
So, for those who might be like myself and are unfamiliar with spiking neural networks, can you explain, what they are and basically how they differ from the traditional neural network solutions that we see powering AI today?
Certainly. I'd love to, show you a video that kind of visualizes basically what spiking neural networks are. So the credits for this video goes to the Howard Hughes Medical Institute. This basically shows the neural activity inside the brain of a zebrafish. And what immediately stands out is the fact that neural activity tends to be sparse in time, and it occurs in sort of a clustered way. So your brain isn't firing all of its neurons all the time. It's selectively different parts of the brain that are lighting up. So as I speak to you, every word that I say causes a different cluster of neurons in your brain to really light up. Every time I say the same word, it's roughly the same cluster of neurons in your brain that lights up. And that's fundamentally what your brain does for pattern recognition. Now, underlying all of that is this neural network called a spiking neural network. It's basically a neural network in which the neurons respond to data by producing simple voltage spikes. And the key in these spiking neural networks is that the timing of these spikes and the distribution of these spikes across the neurons basically encode the information that's coming in from the sensor data. So the way a spiking neural network works is by receiving data from a sensor, encoding it into these simple voltage spikes, and then manipulating the timing relationships between these spikes to either uncover patterns in the data or to actually transform that data to, let's say, improve its quality. So very naturally, these networks have an inherent ability to understand time. They represent time inside of the network. And that effectively allows the neural networks to be much smaller, much simpler, simply because you don't have to use elaborate or very complex recurrent topologies to maintain temporal state. You're now able to maintain that within the neurons and the synapses inside of the spiking neural network themselves. So effectively, this is what makes the network so efficient. The fact that they are small, they fire in this sort of a sparse fashion. And then you have the underlying hardware for these spiking neural networks, which tend to be very efficient. And that's really key to why spiking neural networks tend to be more efficient and much faster than conventional neural networks used in the industry today.
Amazing. And how do you see these spiking neural networks coexisting with current AI models? Do you believe that traditional AI accelerators will, maybe struggle or plateau as far as latency, power, or responsiveness?
Let me answer this question in a couple of steps. So
Mhm.
when you look at the way AI is done today in the world, this is effectively the picture that you see. On the extreme left, you've got the sensor, which produces all of the data, which we use. And on the extreme right, you've got the data center where many of the world's heavy lift AI models typically run. But when data is produced at the sensor, it goes through this journey from your edge device in something like your ring all the way up into the cloud where the big insights are gained. And very often part of the AI model tends to run somewhere in between. Think about the processor inside of your mobile phone. Now, all of these processors consume a significantly different amount of power. At the data center, you consume a lot of power. The applications processor in your phone consumes a significantly higher amount of power than your sensor. The the tough problem generally to crack here is that today much of the sensor data which is generated in the world needs to be moved up into the cloud to be processed, or it needs to be processed on these heavy applications processors. If we were somehow able to make more sense of that data as soon as it's captured, we eliminate much of the power use in this entire AI pipeline. That's essentially what our proposition here at Inaterra is. What we do with our pulsar chip, for example, is integrate the ability to run spiking neural networks alongside traditional non-spiking networks. So in the architecture for the chip, on the top right-hand corner, you see an accelerator for spiking neural networks, and this is what makes us so efficient. But in the real world, when application developers build actual solutions, they very often use stages which might be spiking and stages of the solution which may be non-spiking. And you basically need to have both of them coexisting. So in the larger scheme of things, we use neuromorphic and spiking solutions really to process data at the sensor. And in a larger AI system, we use it to tokenize data as soon as it is captured at the edge, and we do it very efficiently. But I think that there are parts of the pipeline where traditional non-spiking solutions may be very well suited. And there will always be this interplay between spiking and non-spiking approaches. Spiking is inherently very good for time series applications, applications which require continuous processing of sensor data, and non-spiking approaches may be very good for spatial pattern recognition or pattern recognition, which we see a lot in LLMs today. That kind of processing may be very apt to do with a traditional non-spiking approach. So I do see very strong synergies between the two.
Awesome. So I guess my next two questions kind of go together, but I'll split them up for the sake of them being too bulky. But how do, neuromorphic architectures affect, those designing hardware and software, the process of designing hardware and software compared to more conventional embedded AI stacks?
Our entire objective in building Pulsar and building the spiking neural processing technology that we have at Inotera has been to blend seamlessly into the world around a sensor. So if you look at the Pulsar architecture, it's basically structured as a microcontroller. You plug in sensors over standard interfaces. You've got a CPU inside of a chip. And on the chip, you've got the spiking neural network accelerator. So from a system design perspective, you treat neuromorphic compute in Pulsar like you would treat any microcontroller. So you would basically drop our chip in as a microcontroller in your system. There's nothing different from a system design perspective today. Similarly, from a software perspective as well, we've integrated ourselves into PyTorch. So when you're building spiking neural networks, you do that in a familiar PyTorch environment. We've built an extension for PyTorch that gives it these spiking capabilities. But the workflow of how you construct a neural network, how you construct an application, this is basically identical to what developers are used to today, both embedded developers as well as neural network developers. The workflow is basically the same. By doing that, we essentially make neuromorphic computing technology accessible to developers that would typically deploy either a standard microcontroller or a standard AI solution into their system. But as we go forward, there are capabilities that neuromorphic computing brings in that are simply not attainable by traditional processing solutions available in the market. Take, for example, this ability to process time series patterns naturally. That is inherently a capability of the compute fabric, the style of neural network that we use. The moment you tap into that, your system can become smaller. You need smaller memories. What the other possibility that you have is to interface much closer with sensors. So you can make sensing systems much smaller by eliminating a lot of components that you typically find around sensors. So even though today we are a drop-in replacement for a typical microcontroller, as we go into the future, neuromorphic computing with our technology offers us the ability to transform what the entire sensing system looks like. And it gives us the ability to make that system much more smarter, much smaller, much more efficient, and even cheaper.
Awesome. That sounds amazing. And you already touched a bit about the developer's role, but I kind of want to know a little bit more about, where do these engineering teams fit into this new solution? Do you believe there should be a mindset shift when moving from conventional AI to neuromorphic systems?
Definitely. To begin with, I think whatever you can do with a traditional AI system, with a non-spiking system, you can do in the neuromorphic world with spiking neural networks. But the spiking world offers you as a developer a lot more tools. You have a lot of features which basically allow you to solve applications in different ways. With a smaller solution, tapping into time series recognition directly. These are all capabilities which are not there in the non-spiking world. And now with spiking neural networks, you have access to all of that. So the moment you approach your application problems the with the knowledge that you have a tool that gives you these additional capabilities, you may end up at a solution which is much more effective and much more efficient. So that's really the mindset shift. If you had more than what you currently have, what would you do with it? That's really the question to developers. On the other side, basically what we've tried to do with Pulsar and with Telamo is to kind of bridge that gap for developers ourselves, basically by saying that the fabric has all of these capabilities. You don't know how to use them just as yet, and that's fine. We'll provide you with the tooling to navigate that gap for now. But if you invest in this sort of technology and this sort of programming style, you can get a lot more benefit than you're currently able to get with your present solutions. So I think that it's a matter of time for developers to discover what neuromorphic computing offers them and start tapping into those capabilities. And that's actually when we'll see a completely new wave of applications coming out into the market. And all of those will be enabled by neuromorphic compute. And if you actually look at the biological world, it's very curious. If you look into the brain of something like a locust, you see complex signal processing, the equivalent of a fast Fourier transform happening inside of the brain of the locust. You've got specific neurons which are attuned to the sound of prey, and other neurons which are attuned to the sound of predators. And it turns out that the brain of the locust, the really tiny creature, is able to do this sort of complex processing using these spiking neurons. Now, if we take all of those concepts into the microprocessor world, that unlocks a whole new, range of applications. Think about learning. Think about systems which require very fast response. These are applications that neuromorphic computing will be able to unlock, and it basically requires hardware in the hands of developers. And now with Pulsar, we've basically done that. So developers have the chips, and the world of application possibilities is open.
Awesome. So my next question, you probably already touched on a bit, but I always like to know what you, as a professional in your field, how do you foresee this impact of SNNs, in the next 5 years, in the next couple of years, or maybe even in the next 10 years? But the timing is all up to you. I kind of just want to know, how do you see this impacting the near or far future, I guess?
Two parts to my answer. The
Mhm.
first is, I think that we now live in an age where we've somehow normalized measuring compute performance at the data center in megawatts. So not even a unit of compute performance. We're literally measuring compute capacity using the amount of power that the machines draw. I think this points to the general, inefficiency with present day AI deployments. And it really points to the need for a more efficient way of doing AI across this entire sensor to data center pipeline. And in our minds, the only way to navigate this is to move part of the AI to the edge, so that you can sort out the relevance of a lot of data right at the edge, and use the cloud and use the more high powered AI for what they are best used for, insights at scale, the larger models. But treat the raw data at the sensor. And this is basically the first place where neuromorphic stands to revolutionize the world as we know it. It will simply make AI deployments a lot more sustainable, especially in devices that run on small batteries and generate data streams continuously. In the long run, I think what we are tapping into is just the tip of the iceberg of neuromorphic capabilities. We're just using neuromorphic compute today to identify what sensor data is and what patterns inside of the sensor data actually mean. But you could do a lot more. Your brains are able to clean up noisy data. For instance, if you're in a crowded room and it's a loud party and your friend shouts at you from across the hall, you're able to identify that somebody's talking to you, and you're able to identify that it's your friend, and it's your brain that's able to clean up this data and understand the relevance. You're able to learn things on the fly. You don't need to write the letter A 10,000 times before you can recognize and write that letter over and over again. You're somehow able to do it with very few samples. You're able to ride a bike. You learn to balance on top of a bike. These are all very complex operations for machines to do today. And when we apply neuromorphic computing into these sort of applications, I think that there's a wealth of efficiency, a wealth of performance that we stand to gain. And in the next, let's say, 5 years or 10 years, as these markets mature, the need for neuromorphic computing, or rather, these applications and these markets will start to exist because of the ability of because of the existence of neuromorphic processors like Pulsar and the capabilities that they bring to the table.
I am all out of questions for you today, but as always, I want to know if there's anything that you believe I might have missed or anything else you'd like to add.
We're living in a very exciting time. Today, there's so much emphasis on bringing AI to the physical world around us. Our objective at Inatera is to enable what we very cutely call ambient intelligence. So having a world that surrounds us, that is intelligence and kind of seamlessly blends into our being. And the objective here is to make the digital world more accessible, make it smarter so it can serve us better, but also make it more efficient and clean. And the reason why I think it's such an exciting time is that there are so many new, forms of AI, new kinds of technology which are coming into the market. But more exciting than that are the applications that really come out of research. And many of these are really out there. Today, we might think that it's sort of like science fiction. 5 years ago, neuromorphic computing in many of our conversations with customers was labeled as science fiction, something which belongs to a lab. But today we are in production with our chips. We have customers that are basically integrating our chips into their designs and taking them out into the market. And the best thing for us to do is to actually open up our minds and really think about what neuromorphic computing can do, and start using these chips and deploying them more.
Amazing. Well, thank you so much, Sumit, for sitting down with me today and sharing your knowledge and what you guys are up to at Inatera.
Thank you so much. Thanks so much for having me. It was great talking to you.
Thank you. Now, here's Rich and Paul Golden of the Wireless Power Consortium.
Good afternoon. Welcome to the Embedded Executive Podcast. My name is Rich Nass. I am with Open Systems Media, more specifically with Embedded Computing Design. And this week, my guest is Paul Golden, who is the Marketing Director for the Wireless Power Consortium. How you doing, Paul?
I'm doing well, Rich.
Good. The biggest reason that I wanted to bring you on is that for whatever reason, I'm not familiar with the Wireless Power Consortium, which shame on me, I guess, because you have been around for a while. What is it that you guys do? Just give me a little bit of the background.
Sure. So Wireless Power Consortium, which I'll shorten just by saying WPC. It's a lot easier to say. WPC is a standards development organization. And we were formed initially in 2008. Our first standard, which was called QI, was spelled QI, was a standard to provide wireless charging capabilities to smartphones. And as a standards development organization, we don't manufacture, sell, market, or any product specifically. Our member companies do that. And we have over 330 member companies throughout the world. What we do is we develop the standards with our members' help. We manage those standards, and then we certify those as well. So we provide the certification testing to make sure that when people use the standards, they're using them as they're specified and are compliant with the standards.
Is the consortium governed by some bigger body, or are you guys making your own standards and saying we're the law here?
The latter is the case. We are a nonprofit, incorporated nonprofit organization. We develop those standards, and we have, since the time when we were initially founded back in 2010, or 2008, I'm sorry, at that time, there were several standards bodies that were all competing to try to become the sole standard for global wireless charging, and WPC ended up kind of being that position.
Okay. Walk through some of the different standards, if you could. Where are we
Sure.
today? And
Sure. So we have right now, we have actually two standards. We have the original Qi standard that I said was launched in 2010. We launched a new generation of that, Qi 2, in 2023 at CES in 2023. And that was a very important change in the standard. And the biggest thing with that you'd recognize would be it included a magnetic attachment, and that borrowed on the technology from Apple and their MagSafe, and that became incorporated into the T2 standard. That magnetic attachment was very important because it did several things. One, it enabled the device to be more efficient. So a lot of us using wireless charging at times, you had to kind of make sure your phone was sitting directly on the charger. If you were a little bit off center and you put your phone away at night and woke up in the morning, you found, whoa, I've only got 15% charge on my phone. What happened? Well, you just missed. With magnetic attachment, that's virtually a perfect attachment there. So there's no lost energy in the process. It's more efficient and therefore faster from a charging standpoint.
Mhm.
G2 also, when we launched that, was 15 watts charging. So it was significantly faster than the original Qi, which launched at only 5 watts. We launched Qi 2 25 watt here in July of 2025. So that's now taken it up another notch to a faster level. And that's what we were just featuring at CES. But in addition to the Qi standard for wireless charging, we have a new standard called Ki, that's spelled Ki. And this standard works in similar technology as Qi. It's using electromagnetic induction. But the idea here is to take kitchen appliances, any kind of kitchen appliance, small kitchen appliance that you'd plug into your wall, a coffee pot, a toaster, a blender, anything like that, even an air fryer. We've eliminated the need for power cords and eliminated batteries, yet we can deliver up to 2.2 kilowatts of power for those devices. And that was
So
what
you're saying that they would have this charging port embedded into this other device.
So in the case of Qi, there would be a transmitter that could either be incorporated into a dual function induction cooktop, where you'd have both induction cooking and induction cooking with Qi, or could be mounted underneath a kitchen counter or island. So it's concealed. You don't even see it. You don't see it. It works right through your kitchen counter material. Or could be in a standalone induction cooktop unit, which are very popular in Europe, I understand. And the receiver is actually built into the bottom of the appliance. And as soon as that receiver is placed on top of the transmitter, they communicate with each other using NFC. And the transmitter knows, okay, this is something I can send power to, and it will send power based on the exchange and communication between the appliance and the transmitter. Fascinating technology.
It is, absolutely. Isn't the automotive space one of the biggest consumers of this technology?
Automotive space is a big area for us. We have a number of members in the automotive space, both on the automotive OEM side and the charging side. Qi 2 is one of the devices that you're going to start seeing more of in automotive. Unfortunately, automotive and the airline industry is the same sort of thing. They have very long development cycles. So even though we launched Qi 2 a couple of years ago, you're just now going to start seeing products coming out as they change over their designs and incorporate these new devices. What's so good about Qi 2 in a car is the efficiency, the magnetic attachment. You don't have the phone sliding around on your charger anymore. It's going to be, stick right to that spot.
Yep.
And that 15 watts charging is an important feature as well. We have another version of the standard that's not Qi 2 that we call APP. It's a moving coil. Where it doesn't use magnetic attachment, but the coil in the charger automatically lines up with the phone perfectly. And if the phone moves, the coil moves with it. So the end result is the same thing, much more efficient charging, faster charging than you've had before.
Are there a lot of people who make the components for these things, or is it a very small handful of folks who make the devices?
There are quite a few different members of the industry. As I said, we have over 330 members of our organization. Some of those are developing end products like chargers or phones. Some of those are just developing components. So it's a big industry.
Okay. What exactly do you guys standardize? I get there's a power level and there's the magnetic bar. What else is in there that needs to be standardized?
Well, there are two things that standards do that are particularly important. One of those is compatibility. So this industry, and today this industry, by the way, we don't sell, but our members sell over 1 billion devices a year in between chargers and phones. And this industry has been able to grow as it has because the devices are interoperable, they're compatible. So it doesn't matter if I have an Apple phone, I can use one of many different chargers. Or if I have a Samsung phone, I can use one of many different chargers. If you didn't have that interoperability, it would have been very difficult for this standard the industry to grow as fast as it has. So interoperability, compatibility is one of the important things. The other thing is safety. You're talking about electricity. Even though we're talking about 15 watts, 25 watts, that's not a huge amount of electricity. You want to be sure it's safe. And devices that don't go through, that are not using our standard, or they're using an older version of our standard that's available on the website, but they're not certified. We can't guarantee what they're doing. You don't know necessarily what they're doing, how they've made that product, and there have been issues with that. So that's another piece on this. And particularly when you get to something like Key in the kitchen, where you're delivering up to 2.2 kilowatts of power, safety is absolutely critical.
How does the consumer know that the device that they're buying, say it's a charger, is actually standardized and isn't just some knockoff?
Well, that's a very good question, Rich. So a product that has gone through certification testing for us, one of the things that can be done with that then is they can carry the Qi or the Key logo on their device. So it'll be either on their device, on the packaging when they bought the device, or in the marketing materials for that. We also have a database available to the consumers on our website, where if you have a question or you want to be sure that somebody hasn't made a knockoff and illegally used our logo on that, you can go to that database and check that to make sure. And yes, that does happen sometimes where people try to skirt the law a little bit on that one.
Sure it does.
Yes.
What's next on the list of things to be standardized?
So right now we are still focusing on those two standards, but within the Qi standard, we are already working on the next iteration at a higher power level, probably 50 watts, that will be coming out probably 2027. And then we are also working on a standard specifically for smartwatches. This was a big area. We had a lot of people coming to us at CES asking about smartwatch charging and developing a standard for that. And so we have a number of players that are in that industry here, all very interested in coming up with a standard for that. So those are the two big things for us. And then Key just actually launched this last summer. The certification testing was just put in place. The standard was released. So you're not seeing any products in market yet with Key. Usually it's about 18 months from the time a standard is released and certification and testing is available and the time you start to see products in market.
So I have to ask, what's the story with the names of the standards?
So Qi, when it was initially launched, Qi is a Chinese word that means life energy. So I think there was some thought behind that that probably made sense once you understand what the word means.
Okay.
And Key, I was not here when that name was developed, so I can't tell you what took place behind the scenes in developing that. But I think they were trying to come up with something that was similar to Chi, and then I think somebody said Key, K-I, like it's in kitchen. Let's run with that.
Okay, that sounds good to me. Where can people go to get more information?
Well, they can go to our website, wirelesspowerconsortium.com, or there are, for consumers, 2 microsites that would be good for them to go to. One is chargewithchi.com or cookwithkey.com.
Awesome. Thank you very much, Paul. I appreciate your time.
Thanks for having me today, Rich.
That was Paul Golden. He is the marketing director for the Wireless Power Consortium, and I am Rich Nass with Embedded Computing Design.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.